set up I'll just set up a couple of these formulas again. So collisions, you have momentum conservation. And for two particles, momentum's a vector, you have, I'll write it with vectors, plus m2, v2. So that's before the collision, m1, v1 prime. So prime means after the collision, m2, v2 prime. So we have that. And then we had the perfectly inelastic collision, which was when things collide and stick together. So we did a fair amount of that already. But then we added energy conservation. Which is not always applicable, but when it is, then you have the sum of the initial kinetics equals the sum of the final kinetic energies. So equals and have m1 v1 prime squared, m2 v2 prime squared. So we had to solve these two equations, and we did. And we ended up with v1 prime and v2 prime in terms of, so we found these final velocities in terms of the initial ones. And that's where you guys can help me out. So what did we have here? I know the denominator is always m1 plus m2.
We had m1 minus 1, m1 minus m2.
There we go.
We have v1
Times v1
plus 2
Two.
m2
2m2.
over m1 plus m2.
Fantastic. And once we found that one, the second one we could get just by changing everything here, exchanging all the signs. So then we would have had m2 minus m1. Oh, actually, since I'm doing it in terms of,
Wouldn't it be 2 m1 v2?
yes, because we wanted to do it in terms of, in that same order. So 2m1 v1 m1 plus m2. So this one we just wrote down that way. The fact is, you do the algebra, of course you can get the same thing. And then we would have had plus m2 minus m1. I didn't bring those demos again, but I'm going to refer to them. v2. We pointed out that could be a matrix transformation, right? If we wanted to, which we're not going to do that. But now, this is as far as we got. I showed one case, and now I just want to go through those a little more carefully. So, the first example, and this is what we ended up with, would be m1 equals m2, v2 initial equals 0. Because that's the one we're always showing when we send something across the track, collides, and so forth. So, actually, here we add this. So, then for one dimension, that's what we got here. Okay. So yeah, and so we go back into here, and we're looking for v1 and v2 prime. v1 prime, got m1 equals m2, you got a 0 here, this was a 0 there. So this is the one that came to a dead stop. And v2 prime, this is 0 because of the equal masses. Then we have 2m1, m1, so 2 over 2 is 1. So v2 prime equals v1. So that was the case when it's that prototypical one. You have that equal mass. This one comes in, dead stop. This one goes flying out. You notice all the other cases when the masses aren't exactly equal get much more complicated. But that's a important one to look at. The other important case that we were talking about is, suppose v2 equals 0, and this time m1 and much greater than M2, and you get something kind of surprising. In this case, so now we're going back to the V1 prime and V2 prime. So V2 is 0, this is gone. M1 is much greater than M2, so this is essentially slightly different than M1 over M1. So if we do an approximation, this one is so large it doesn't really change its speed very much. So I'm just going to say approximately equal to V1, V2 prime. V2 is 0 again, so we can ignore that one. Now we have 2M1 over M1 essentially. So V2 prime is approximately 2 times V1. And this was that phenomenon we saw that the big one comes in rolling in slowly and kicks the other one out faster. Okay, triumph of theoretical physics, right? So, because we just asserted these two laws and then we get these phenomena. Now you could ask for things that we haven't seen, and this one's interesting, I think. So we're going to have V2 equals minus V1. And again, M1 is going to be much greater than M2. So what are we looking at here? We're looking at a head-on collision. So we're looking at a head-on collision, except this one here is colliding with that one there, right? They're headed towards each other. One's much larger than the other, much more massive. And let's see, we'll take some spaceship over here and see what happens. So we'll have V1 prime, M1's much larger than M2. So, you know, we still, we're going to be very approximate about it. M1's much larger. So this denominator makes this very small. Makes sense? So we're going to ignore this one. And so V1 prime is still approximately V1. But now what about V2 prime? We're going to have V2 prime yeah, this is good. So V2 prime, we're doing approximation again. Same thing as before, we get 2M and M down there. So it's approximately 2V1. But this one here now we have a minus sign dominating, so we have a minus M1 over M1 essentially. The M2s are small, right? We have minus M1, V2 is negative V1, so that gives us plus another V1, so approximately 3 times V1. So there's a famous and fun demo. Have you guys ever bounced the tennis ball off a basketball?
Yeah.
Class. You've done that. Okay. Yeah, so you drop a tennis ball and a basketball together, and you know, they hit the ground, and the tennis ball is launched to a great height. Have you just seen that one before? Yeah. If you do it pointed away from your eyes, say you have a tennis ball and a basketball at this height, and you drop them on the ground. If the tennis ball is pointing toward you, you know, put your eye out, okay? Because it's so fast. It gets launched really high. That's really that effect right here. You're getting maybe 3 times the initial speed, so that's 3 times the bounce speed, right, of the basketball. The ideal basketball would bounce this size and drop, right? So if something has up to 3 times the speed, that's 9 times the height. So it's going up there. Okay? So if you drop it from say chest level, 9 times chest level is way up there. So anyway, that's an interesting example of this as well, that opposing collision. Good. So what else do we have here? Yeah, then I brought this. Oh, actually, before I show that, let me just show the kind of problem we can do with this, because we're going to save these for next semester. but, I'm just gonna call this more examples. So for that last homework problem, we said we would have a ball hanging here and we'd just swing, let one swing in and collide. Right? Here we said they were going to collide inelastically, and then we're gonna find that, you know, if they don't go that far up there, they'll be like this. You know. Right. So that was that problem for the inelastic one. What if we have elastic collisions and drop them like this? What do we expect? So in the instant that it collides, it's just a one-dimensional horizontal problem that we have here. So we could say, whatever speed it has as it comes down here, which is really, I'll just call this h1, you know, or just h. V root 2gh, right? Comes swings down there. So if these are equal masses, this will come to a dead stop, and this one will swing up to the same height. If this one were much larger, it would pretty much plow through, but this one would be launched twice the speed, so it's 4 times the height. So all of these things could be applied to this interesting system as well. And if this one were much larger than this one, what would happen? Actually, we'll talk about those right there, but what's your anticipated result if this one is much, much more massive than this and this one's at rest? We should talk about that.
Smaller ball will bounce off it.
Smaller ball should just bounce back, and if this one's large enough, it won't do much at all. So actually, that is a good one to check here. So that's another example. Under these, we could have M1 much less than M2 and V2's at rest. So if M1's much less than M2, what do we get here? Then our V1 prime, this one's 0 again, M1 much less than M2. So this just makes it very small. So I'm just gonna say approximately 0, very small. And then V, no, my bad. Much less than M2.
V1 prime is approximately negative V1, right?
Yes.
And V2 prime.
Oh,
would be
I was looking at the
zero.
wrong one. So M1 right here, I was looking at the wrong M here. So V1 prime, M2 is dominating. M2 over M2 with a minus sign, approximately minus. So that means it just bounces on. Okay, good. So yeah, we can play with these examples a lot and do some interesting stuff. I brought this device to class. Not everybody has seen this thing in operation.
It's quite old, right?
Yes. And we're trying to have elastic collisions in their properties. And so if you build one of these, make sure you use a really hard steel of some type. We had years ago, our shop guy built one of these, but he used cue balls, billiards balls, or something like that. And it didn't work at all. It just sloshed around after a few, because it was not sufficiently elastic. But here, this one I think is pretty good. So what you're getting here is a transfer of momentum and energy through this contraption, so that you release one here, and you get one on the other side. So here's where the fun begins. You do 2, and the one in the middle remains at rest, right? So you do 2, and you're balancing energy, or no, you're conserving momentum and energy in order to get these effects. So the material chosen has to be pretty good. Actually, this is the third one is where the fun begins. Because if I release these 3, what's going to happen?
So you will go pretty fast, right?
You got to conserve Yeah, is this gonna be the large mass that kicks off the two small ones faster? It's always 3 and 3 on each side. And apparently that has to be the case if you conserve energy and momentum. Like you could say conserve energy by having these two get launched out with much higher speed, but that wouldn't be conserving momentum at the same time. And 4 is even better for this effect. It's just switches back and forth. It's always 4 that come in at a certain velocity. Those 4 have to move out, and the so there you have it. These are pretty good. That's a crowd pleaser. The average always takes us out there to grade plane. So that's really demonstrating these things we can talk about. So after one dimension, we start doing collisions in 2 dimensions. Yeah. I guess I'll return to the perfectly inelastic retards. So momentum is going to be M1V1 as before. I mentioned this before. So I'll just put this in here for the record. So the perfectly inelastic do not have energy conservation. And we can do something like this, M1V1, V2, M1 plus M2 V prime. And then recognize that that is literally just a triangle. This vector sum, for example, if we're coming in at right angles, we're going to go off there in some direction. But since these are just 3 vectors, we'd be looking at this, this, and that. So to the analysis of fucking the analysis of the triangle is enough to tell you everything you can know about the collision. And if you do check the energies before and after the collision, you'll see there's quite a bit of energy. There's a major energy difference. So yeah, we talked about those, but always good to remember because you're just setting up a triangle. You don't have to be confused about it. Set a triangle, label it with what you know and what you don't know, and then just go ahead and solve. It'll allow you to solve for 2 quantities. Now, if you're doing the elastic collision, then we actually have to look a bit at what kind of information we have available. So let's go ahead and just write this down. This again. And count equations. So we have M1V1, M2V2. So that's the before and after of that in terms of momentum. That's 3 equations. And we have the other one, kinetic energy. And so we have 4 equations. But in 3 dimensions, in space, how many unknowns are there? You could say, before we're looking at B1, B2, and after that we're trying to solve for B1 prime, B2 prime. So what that means is there are 6 unknowns, and there are only 4 equations. Okay. 4 equations for 6 unknowns. What does that mean?
Have some 3 variables.
Give up? Can't solve? We don't have enough equations to get a unique solution to the problem. It means that at the level of point particles, the outcome of the collision isn't fully determined. It's determined up to 2 unknown quantities, and those could actually be, well, they could be anything depending on what you do know. Okay? So, point being, we have 2 unknown quantities in the collision. So that would be, so let's go ahead and write this down. So for the collision in 3 dimensions, we have 2 unknown quantities, or two equations, 2 cubed. Okay. For the collision in 2 dimensions, then we have 1, 2, 3 equations for 4 unknowns. We have 1 unknown, and in 1 dimension, we have 2 equations and 2 unknowns. 1 dimension is the one we just solved. So that was the one that can be solved exactly without knowing anything more about the system. So in 2 and 3 dimensions, you have to know more than just the point particle nature to completely predict what's going to happen. I'll give an example where we can completely predict. We'll do this next semester's homework. Okay. So, point being, here we have too few equations to just learn everything from the collision there. But in, the straight line collision, then we actually had everything determined. Let's here's a nice example. This one is actually 3 particles colliding. Let's look at this next example. I'll probably assign this next semester for the moment. Imagine that now we have a particle 1. So we're going to have 3 identical particles. Now, generally speaking, 3 particles would be worse than 2 in terms of how many equations you need. But this one's coming in here, and it's going to strike. So we have to do some geometry here. So if we have particle collision like this, we have an equilateral triangle geometry. The particles have the same size. Okay? And under those circumstances, they're perfect spheres, so they're only touching at one point. Then you can actually know the angle. I should make this picture bigger, but we're just going to run with this one. You can know the angle at which these guys leave. In fact, okay, you can know the angle because if these 3 particles touch like this, in one point of contact, that's essentially a central force, right? At that instant in time, it's kicking it out in that direction. So you know these angles, and then now you suddenly have plenty of information. And And then you say it's a symmetric problem, so what this particle does, this one does exactly the same thing in the, in the lower direction. So here you can have plenty of information, but that's kind of getting ahead of it, but it's a nice example. So the next thing we're gonna do is set problems up in 2 dimensions.
I have a question.
Yeah.
Can we use a similar kind of symmetry, but like with particles in 3 dimensions to get more equations?
But yeah, but see, in this case, instead of points, we know that we have spherical. We can. Okay? If instead of just a point particle, we say it's a finite sphere, they're the same. Then it's like playing billiards. Then we actually have something that's completely determined. So yeah, that's the one I want to set up next. This example is always nice there. With the equilateral triangle. But yeah, so 2 dimensions. These calculations are so important. You guys remember the Compton effect? Yeah, we'll do that one next semester. It's actually relativistic, but it's a nice one to set up like this as well. Anyway, so now we have a 2-dimensional system. We have M1, V1. We have an x-axis here. We're gonna have a target this time. Next semester we'll go into the center of mass range. We have M2, comma, V2 equals 0. And so before the collision, this one's coming in at this target after the collision. One of them goes in this direction, M1, V1 prime. One of them goes down here, M2, V2 prime. We can have, say, theta and phi as these scattering angles. Okay. So yeah, in this case, momentum conservation gives us M1, V1 before the collision. After the collision, we're just along this x-axis with M1, V1 prime. Cos theta, M2, V2 prime, cos phi. So here we're going to carefully select our equations here. In the y direction, we had 0 momentum before the collision. So as these things scatter up and down, their y components are going to be M1, V1 prime sine theta. And because of the way I'm labeling it, I'll put the minus sign as I hand here, minus M2, V2 prime sine phi. And then for energy, we will have, I'll write the halves in, V1 prime squared, here we'll have a half, no, not prime, V1 unprime squared, 1/2, M1 V1 prime squared, half, M2 V2 prime squared. So yeah, what are the unknowns here after the collision? We have 3 equations, but we have V1 prime, V2 prime, theta, phi, all unknown. So we can't know all 4 of them just from this calculation, because we're just sending point masses at each other. What about this one on the left now? I think this one has so much information. We have 3 identical particles. We're going to collide in an absolutely identical or symmetric manner.
So it's only the first particle is moving?
And yeah, initially only the first particle's moving, and then so 2 and 3 are at rest. That's 1 after the collision. So the momentum on this one, and by the way, this is, this one is colliding with a particle twice its mass, but because it's lined up in a certain way, we're pretty sure it's going to bounce back a bit, but we don't know with what speed. Okay, because this isn't quite the 2-particle solved. So momentum, we say M, they all have the same mass, so M V1, it's going to be M V1 prime. Okay, that's what it does, forwards or backwards, we don't know yet. As far as these go, it's gonna be symmetric, so we're gonna have 2M V2 prime. Right, 2 and 3 are gonna have the same speeds. What's the angle going to be? I'm just gonna call it theta. It turns out if you work a problem like this, it's better than using the, say, the cosine of 30 degrees, okay? That's just the number of magnitudes. But theta, the point being, theta here is known. Theta is known. So since theta is known, we have two unknowns in this equation. And the energy, we have a half m v1 squared equals a half m v prime squared plus v1 prime squared plus 2 1/2 m v2 prime squared. Again, because of the symmetry, this one, 2 and 3 are doing the same thing, just twice. So this problem, which looked a lot more complicated, or is in its general form, but in this highly symmetric version, has two equations and two unknowns, and you can just knock it out. It's not that bad. Turns out that this one does bounce back a bit with a certain speed. There's definitely nothing you can guess the answer to. But that's what having something known about your system brings into play. At this one, we just have these point masses, so we don't have enough information to solve it completely. But this is a classic system where you have detectors and you're trying to discover the properties of this thing. For example, the particle you launch in here, in the Compton effect, if you remember the Compton effect, what was it?
It basically proved that light is particle.
And the particle nature of light, you actually have an incoming incoming gamma quant, or I don't know if it's gamma or not, but incoming light particle, photon, right? And the beauty of it is you're treating it exactly as though it were particles colliding. So you literally set up this picture and do the calculation. And then what happens is the incoming photon is scattered, and there's a shift in its wavelength. And the shift in the wavelength depends on the angle with which you measure it with. So yeah, we'll do that one next semester. The thing is, it's relativistic. There's a couple ways to do that without having done relativity yet. We'll see. So yeah, it's the Compton effect. What about the Rutherford scattering? I'm just going to put these, even though they're not exactly next, they're a little bit downstream, but Compton effect. So the Compton effect is scattering photons and you're scattering them on off of electrons. And it's a relativistic calculation, but there's a nice approximation to it where you can at least use the 1/2, use the classical electron momentum and energy. So that's the one. And the other one is Rutherford scattering. And you guys remember Rutherford scattering was scattering alpha particles off of gold foil and gold nuclei. So I'm gonna set that one up for us. That's what we have to look forward to next semester on both of these. And in the meantime, next semester we'll do another problem. type as well, but I just wanna show where this all is heading. So, okay, so the Rutherford experiment. You have charged particles. So this has M and Q, so mass. Comma. It's coming here and it's heading towards the gold nucleus. Now the thing about the gold nucleus is that since it's part of the gold foil, you can treat it as being immobile, so it's not gonna go anywhere. And it's these doubly charged helium atoms, these alpha particles that are going to scatter. Okay? But you have a charge here, so we'll just say Q1. I'll use M1 and Q1, so now you have a mass and electric charge. And the idea here is that you have a nucleus, so you have potential energy Q1, Q2, or 5 epsilon naught R squared. So you know the interaction. You know the interaction, and if they're both, the nucleus is positive, the projectile here is positive, then you have a repulsive force, and so if this thing comes in like that, it's gonna veer off. That's the idea. And you can set detectors up here and measure it coming in, and you don't just send in one, you send in the whole stream of particles, and then they go off at different angles. Why would they go off at different angles? You're gonna set your detector up here and measure the number of particles at one angle and the number at different angles, and so forth all around. So if you're just treating this like a perfect Coulomb's force system, we get another picture going over here. And what you have is take an axis here, and here's our center of potential origin, okay? Depending upon the distance from this axis, we have something called the impact parameter. So if you launch something here, it's gonna sweep out like that, say. If it's closer, it will actually interact more sharply at a bigger angle. If it's farther, it's a slighter angle. If it's farther away, it will veer off less. So there is a point of closest approach. And what we're looking at is the application of the central force problem. So we're gonna do a central force problem where this is just a repulsive force, so it's going out that way. Those will be the hyperbolas that we didn't deal with yet, when we were doing ellipses and central force, okay? So there will be an angle here, and an angle here. This would be the one that you actually measure as you swing your detector. You've got a detector up here, detecting the particles coming in. You got a stream of particles coming in. They go this way, you got a detector. And if this is just a pure Coulomb force, there's a very well-defined expectation of where these things are going to be, depending upon the impact parameter. So this would be scattering. And so over here, I'll just say, we have a stream of particles detector. And this would be the scattering angle, theta equals the scattering angle. And we'll do this next semester, so, you know, we'll imagine we have a certain annulus here. The particle are going through 3 dimensions, and that annulus will correspond to a certain range of particles at the detector. So that's going to be the scattering chapter. And the assumptions are going to be will be that we have m v naught at negative infinity, right? And the other assumption will be u equals 0 at negative infinity. And then the assumption will be that we have a central force interaction with these particles. And so with those assumptions, we can get a relation between what's going on over here and what's going on out here. And then that's what's compared experimentally. And if it just keeps working, the stronger you make the, what happens if you have a head-on collision with this system here? Like absolutely head-on. Gonna come right back. Unless it's so tough. If it's a little bit to the side here, it can blow through now. But if you have an absolute head-on collision and you have this potential with an immovable center of potential, then something flying in should actually go straight back. And that's what Rutherford meant. Not that it comes straight back, but that he was finding at these large angles the occasional event that had to mean that the Coulomb force was in operation down to 10 to the minus 14. That's how that came into play. Anyway, we're gonna do that. We're gonna have plenty of time to do that next semester. It'll take us back to our central force formalism. But for now, that's all we've got. Okay. Are we meeting at noon today?
Are we?
Do we have anything?
No, for 170.
For 170, we have something?
No, not for 170.
We have nothing for 170. Well, let's think